Pronto, acho que estou tentando colocar o YouTube. Agora foi. Eu fico sempre confusa para clicar todos esses botões. Ainda não me... Agora foi. O Dominique ainda não está, né?
Não.
Então vamos falar em português. Mas que bom que saiu esse assunto, porque...
Quase que a gente perde a palestrante.
Então, assim, eu imagino a gente falar, ligando para você às 3, você na praia, na piscina, está correndo na piscina.
Como é que te ouve?
A Zezé pensou que a palestra dela fosse às 4.
Ah!
Estava toda organizada para as 4. É porque os 2 dias anteriores a palestra era às 4, né?
Sim, mas a gente...
O último horário?
O último era às 4, mas o último é para a gente brindar. Então, a gente organizou para terminar mais cedo.
Eu não sei como é que essa história do brinde, me explica aí como é que é. Você conseguiu fazer aquela coisa que entra não sei em que lugar e que parece que você está andando?
Não sei, não. Isso eu não sei fazer, não, Zezé. Cada um vai... Eu vou abrir a minha garrafa aqui e vou... É rudimentar, vai ser um brinde rudimentar. Cada um abre sua taça. I think we should change to English, maybe.
Okay.
Yes. So we are discussing about the...
Oh, you don't have to. I like to hear the musical sound of Portuguese.
Yeah. All right.
But I don't see the speaker. Where's Dominic?
Yeah. But you still have...
Steve,
What?
You know that your screen, Steve, your screen is interesting. You are, how you say this, com saudade from the meeting in a bar. Look at.
Well, yeah. Yeah. You know, these talks are difficult. They're very difficult. I need to be near a bar so that, you know. I can...
So you are ready for the toast already. We are discussing that how you be the toast. So you are ready.
Oh no, this is a coffee bar. You see, this is morning. For the toast, I will switch to probably what is it? It's somebody has these pictures on a patio having, you know, some wine by the river. Who would that be? Not Monet. Who's that other guy? Impressionista.
I don't know.
Oh, yeah, you do. Anyway, I am ready for the toast.
Very nice.
Dominique is here, Isaiah.
Dominique is here. Perfect.
So,
I don't know if...
Jacqueline, explain for me. Once we start...
I can be the chair, but also Catherine can present Dominique.
Oh, here's Dominique. Dominique.
Yes, since she's here, well, if she wants.
Do you want to present Dominique, Catherine?
I can, yes, of course.
Great.
Because it's...
But, no, I will see because my internet is not very stable. So if I disappear suddenly, then it's not my fault.
Okay.
Don't worry.
If you disappear, Isaiah take over, don't worry.
Yeah, don't worry.
That's good. Thank you, Catherine. Zezé, you were asking me something? I'm sorry.
No, what we are talking right now is already in the YouTube, in the live, it's like this, or you start when you wish? How is this?
It's live on YouTube now, but in the channel.
Okay.
But then we erase everything is live now. But we erase these and we leave just the talks because I'm recording the talks.
Okay.
Dominic, do you hear?
Hi, everyone. Just a second. I have a small...
No problem.
technical difficulty with connecting my my tablet to the meeting. Okay.
Maybe the easiest way is to enter twice, once with your tablet, and I don't know.
Yeah,
I have problems with the tablet every 2 months, and you need to update, check always the updates. Well, in my case, I always need to update the tablet because always the first thing which doesn't work is the is sharing on Zoom. So I don't know.
Yeah. Oh, okay.
Ok. Then, Jacqueline, send me the password to this and the ID of the meeting, because if I have to enter on my computer and my tablet, there I must have the password and the ID for the meeting.
Ah, okay.
You know,
Okay,
you
I
send me. Okay.
I'll send you.
Through WhatsApp. You just send through WhatsApp. That
Okay.
is fast.
Okay. No problem.
Thanks.
Okay, Jacqueline, is screen sharing
I'm sorry. Yeah, it's not. It's not. It's
okay.
I apologize. I'm still a bit confused with all the. I guess you can do it now. Do you have two users now? So maybe I have to allow you twice.
Yes. So please.
Yeah, I'll do it.
Yeah. Just.
I think now it's fine.
Okay. Yes. Everything is okay now. Okay. Yes. So okay. Sorry, I'm ready. Let me see. I hope you can all hear me well and see me well. Good morning. Good to all of you who still have
good morning.
Good morning, Dominic.
Yeah, good to see you or to hear you. Just yeah, I'm ready. So yeah.
Okay, Jacqueline, then I start introducing Dominic Kwietniak. It's a very pleasure to have him talking today. He was visiting Fundong several times, I think 1.5 years or almost 2 years on as a postdoc about a couple of years ago, teaching, lots of interactions with students. Now, well, for this reason, but not only, there are now a couple of Brazilians in Poland learning Polish, at least 2 I know about. It's very great to make this connection. So I'm very pleased to introduce Dominic Kwietniak.
Yeah.
I'm looking forward to your talk.
Yeah, so thank you very much. Let me just say that well, as Katrin said, I've been for almost 2 years between 2015 and 2017 in Rio. It looks like it was just a while ago, but this is almost 6 years. This scares me a little bit how fast it goes. The time flies, and I'm super happy and excited that I can participate in this birthday for a graduate program at UFRJ. That's a great honor and pleasure to talk. It's a bit pity that we cannot meet in person. Well, especially that we have now a very nice winter here. So, well, quite a lot of snow compared with the last few years. Okay, so let me begin. I hope what I write is visible for you. Is there's the guiding question for today's talk is how to measure the distance between orbits. So as the title suggests, what I will try to do is I will try to answer, to give you some possible answers to that question and to discuss what are possible applications of those answers, because there are some. Let me mention that this is like there's no single paper in which all those results are contained. It is more like an overview of a few works. I have pleasure to write with some co-authors. So to mention those co-authors is Function Tsai. This won't be an alphabetical order. Jian Li, Habibe Furlan, Felipe Garcia Ramos, and Marta Wąska, and finally Piotr Okrocha. So, and of course, I will also mention work of other mathematicians. But yeah. So we consider the very usual situation in which we have a continuous transformation T acting on the compact metric space. X rho is a compact metric space. So the most common setting for doing dynamics. Of course, T is continuous. And this should be clear that whenever we pick 2 points, X and Y in our space, then of course, those 2 points being close doesn't tell us much about the behavior, because okay, dynamics is all about asymptotic behavior at infinity. So we are really interested in the long time behavior of orbits. And measuring the usual distance between 2 points, it just tells us that those 2 points are at time 0 close, but doesn't tell us much about future of our system. So one can what is now the simplest way we can take into account that we would like to measure distance between orbits? Well, the simplest way we can really apply is we can define, using dynamics, we can define a supremum metric, which just asks us to take supremum over all possible iterates of the distances between corresponding points on those orbits. So we can define this notion, and now we have an option to take into account the future of our system. So the behavior at infinity is somehow reflected by our new metric, but unfortunately, what can happen is that we lose connection with the original topology of our space. So what I mean by losing connection with the original topology. By that, of course, I mean that, well, our new metric may not be compatible with the original metric given by the metric rho. So it is not that easy. But, well, what happens if it is? So this is not my result. This is a very classical part of topological dynamics. So if rho sub is continuous with respect to rho, then xt is called an equicontinuous system. Well, the name can be explained by this observation that, well, continuity of one function with respect to the another means that for every epsilon greater than 0, we can find delta greater than 0, such that the distance between 2 points smaller than delta implies that this rho sub between those 2 points is smaller than epsilon, but this really means that for every n greater or equal than 0, the distance between t and x, t and y is smaller than epsilon. And this later condition here, this is called the family of functions Tn, when n is greater or equal than 0, is a continuous family. So when we play the game of proving that the map is continuous, then we are given epsilon, and for that epsilon we should choose delta. And it turns out that actually we have such a family of maps that not only for each of those maps is continuous itself, but we can actually pick, given epsilon, we can pick delta, which will be good for all those maps. So they are continuous in the same way. And then there is a classical theorem. I think it goes back to Halmos and von Neumann, but okay, the Halmos and von Neumann theorem, it has two versions, one for the measure theoretic case and the other works for the topological case. So this is topological Halmos von Neumann. A system xt is equicontinuous if and only if there exists G compact topological group and an element small g in G such that xt is topologically conjugated with a system GRG, where RG from G to G is the rotation. So it takes X in G and maps it into G times X. It's a rotation by G. So actually, equicontinuity for a dynamical system means that this system is just a topological version of a rotation of a compact group, and this group, well, has to be necessarily abelian, and this rotation is actually well, changing a metric, we can make sure that our group is isometric action, meaning that there's a metric compatible with the topology on our space such that our action preserve this distance. So okay, so this is like a prototype of what I am talking about. So let us take a look again. We started with a compact topological dynamical system, and we invented a method of measuring distance between orbits, which led to a new notion, new metric. And then when we checked for which system this new metric is compatible with the old one, with the initial one, we obtained a nice characterization of a class of systems which are, in fact, very, from the dynamical point of view, compact group rotations can be considered as simple systems. And whatever I will tell you later, it is also a kind of a theory which helps you to understand systems with low complexity. So this is somehow the whole story of measuring distance between orbits turns out to be good for systems with low complexity. But okay, still, this is like a typical situation that whenever we start to talk about, well, we now think about two orbits more like two sequences of points. So if I take point X, then I can create actually a sequence of points Tn of X when n runs over non-negative integers. This is more like an element of the space of all one-sided sequences with values in the space X. And now, okay, now we are talking about spaces of sequences, and this is not surprising that for spaces of sequences we have more than one interesting metric or pseudometric we can consider. So the next step is one can define Besikovich pseudometric, and if you want to measure the distance, the idea goes as this.
Sorry, Dominic, the first metric was the metric, or was it pseudometric, or the first metric you introduced is?
I think it is I think it might be even a metric. It might be a metric still, but usually it is not compatible with the.
Okay, it's not the equivalent or
to the topology. So that's the point. So okay. Even if this, so because usually it is not equivalent, then we don't bother. So now what is the point? Because we would like to measure distance between orbits, then we are not that picky about the situation in which two points from the same orbit are at distance 0, right? Because after all, we really would like to talk about behavior of orbits more than about behavior of single points. We think of a point as a part of a bigger object, which is an orbit, and we are really interested in the interactions between orbits. So pseudometric is a function which is like a metric, but we do not require that the distance is 0, even only if we measure a distance from a point to itself. So This is okay. And what do we do? So to define this Besikovich pseudometric, we take 2 points, and then what we will do for each n, we measure the average distance between the initial segments along the orbit. We take those 2 orbits and we measure. So we have x and y, t of x, t of y, t square of x, t square of y, and then we measure. Well, here we have distance, here we have another distance, and here we have another distance, and we just take the average of those. So this is here what we have defined. This is the average, but this measures on. So this is a metric. For each n, this is actually a metric, and because t is continuous, this metric is actually even still compatible with the topology. But because we are really interested in the behavior at infinity, then we really do this usual trick of extracting information at infinity. So we take the upper limit. And because of this taking upper limit, it may happen that there are 2 different points which are still at distance 0, which are still at distance 0 from each other, because this lim sup is going to 0. So think about a pair of asymptotic points. A pair of asymptotic points certainly will go, this lim sup will certainly be 0. So now we can introduce a notion which is also it's also quite old. It goes back to a work of Sergei Fomin from 50s, and then Joe Auslander studied it at the end of 50s. So quite natural notion. It is like this a topological dynamical system xt is mean equicontinuous if this rho b is continuous with respect to rho. So this really means that, again, for every epsilon, there exists a delta, such that if we have 2 points in the space with the initial distance smaller than delta, then the Besikovich distance between those 2 points is smaller than epsilon. And well, the first thing we should note is that, well, if a system is equicontinuous, then it is really mean equicontinuous. So this is a nice thing, and maybe a little bit more work is required to see that there are systems which are mean equicontinuous, but not equicontinuous. For example, Sturmian systems. So this is like if you take a symbolic codings of irrational rotations. So you take your circle, you mark your irrational, your interval from 0 to alpha. Alpha is irrational, and then you agree that you will take the orbit of 0 with respect to the rotation by alpha, and then you encode it depending on whether your point of this orbit is in the interval from 0 to alpha, and then you put 1, and if your orbit visits at time n this complementary interval, then you actually pick the symbol 0 at that coordinate. So in this way, you obtain a sequence of zeros and ones, and when you take the closure of the sequence with the orbit closure of the sequence with respect to the shift, you obtain a so-called Sturman system. And Sturman systems, they are not rotations of any group. It can be proved that they cannot be equicontinuous, actually. Well, one of the reasons is that in any shift system, you have to see some asymptotic pairs, and in the equicontinuous system, they cannot be asymptotic. Because if you turn this equicontinuous system into this isometric system, then you see that no pair can be never asymptotic, because the initial distance is preserved if you have isometric system. So you see, we have examples, and actually that there's a theorem saying that mean equicontinuous transitive systems are so I think this is theorem due to the Doppler cluster. Mean equicontinuous transitive systems are minimal topo-isomorphic extensions of group rotations. So, every minimal system. So every minimal system. So how to understand this theorem? It is like if you have xt minimal system, then for every minimal system there exists the so-called maximal equicontinuous factor, and the maximal equicontinuous factor is the largest factor of the system, which is the group rotation. So some systems, they necessarily have only trivial equicontinuous factors, but some systems have non-trivial equicontinuous factors. For example, Sturman system, which I presented before, has the rotation of the unit circle by alpha as this maximal equicontinuous factor. This is largest possible equicontinuous factor. You can imagine that in every minimal system, you can always find the largest possible rigid part. And this is represented by this maximal equicontinuous factor. And of course, this is a topological factor. So this is like a surjective continuous map. But it may happen. So the map, which is topologically a surjection, is always measurable in one direction. But when you consider measure theoretic isomorphism, then for measure theoretic isomorphism, it is not important that a map is not invertible on some subset of the phase space, provided that the subset of this phase space is small with respect to the measure. So topoisomorphism extension means that there exists a topological factor, which is in the measure theoretic category and isomorphism, which means that those fibers here, which are mapped onto single point here, they are negligible. And because when you see that situation, then you see that this minimal system above has to have a unique invariant measure, so it's still uniquely ergodic. And as a measure theoretic system, this is isomorphic to a group rotation. So we see that the mean equicontinuity allows you to distinguish well, a special class of well, models of group rotations. So let me introduce some more vocabulary. So let x mu t okay, it can be measure preserving dynamical system. So we just assume that X is a measurable space, Hartley X is a sigma algebra of subsets, mu is an invariant a probability measure, and T is a measure preserving transformation on X. And a topological dynamical system, YS, is a topological model for X mu T if YS is uniquely ergodic. What does it mean? It means that the set of ergodic invariant measures consists of a single measure, and this is the unique invariant measure for the system. And if we consider Y with a Borel sigma algebra, nu this invariant measure and as a transformation is isomorphic to X. So well, of course, this system, to have a topological model, this measure preserving system we begin with has to be ergodic, but when we start from an ergodic system, then there is a theorem saying that actually this is a very nice theorem because it says that whatever you would like to consider in the category of measure preserving system, you can always find an topological realization, meaning that you can always find a topological system in which will have this invariant measure, well, as the unique invariant measure. So in some sense, it is well, measures invariant for homeomorphism of compact metric spaces. The family of measures invariant for the homeomorphism of compact metric spaces is not richer than the family of abstract measures preserved by measure preserving systems. So this like pure ergodic theory is not richer in measures than measures realized on measure preserving on topological systems. Of course, you have to remember that you have to assume some regularity properties of these measurable spaces, because otherwise you may not see those measurable spaces isomorphic to any compact metric spaces. But this is really...
Sorry.
Yes?
Sorry, Dominique, I have a probably very silly question, but if you start, for instance, with an OSOF diffuse in the torus with the Lebesgue measure, what is the topological model of this?
Well, there is a theorem which says that you will find a compact space. You have to build the space. So this is a bit abstract space, but I think that because an OSOF diffeomorphism will have a finite measure, then actually you will find a shift space on which will be minimal and which will have the unique invariant measure, which will be isomorphic to the Lebesgue measure for this ANOSOF. So this is a way of extracting from this ANOSOF system only one measure. So you have to remember that we are kind of building a topological model for. So we are ignoring a lot of information we have in this Anosov system. So this will be a shift with some Bernoulli measure with that given entropy.
What is a reference for those type of results?
It's I think it's called the Jewett-Krieger theorem, and
okay.
I don't remember right now a reference, because it was proved in a few stages. So first there was assumption of weak thing needed, or anything like that. So yeah, I don't remember. I'm sorry, I don't remember this.
Yeah, that's perhaps
the latest work by Weiss. So
Dominic, can I also ask you a question?
Oh, sure.
The question of me was the Jewett-Krieger theorem. What kind of models do you get there? So as what kind of systems can you construct this stuff? So so basically, the model, to which kind of class does it belong to?
So basically, I think for the finite entropy, you just take symbolic models, because you find generating partition, and you just take care of copying this behavior on a generating partition from your system to your model. So the result sounds very, very abstract and counterintuitive, but oh, thank you, John. He's writing a reference on the chat. So thank you.
Nice.
Yeah, it's our intuition is here, I think, fooled by the fact that this isomorphism of measure spaces is nothing like a continuous deformation of those spaces. So remember that if you take like any invariant measure on the compact metric space, not any probability measure on the Borel sigma algebra of a compact metric space, then you can always find an isomorphism to the compact interval and the Lebesgue measure on the Borel sigma algebra, restricted to the Borel sigma algebra. So when you are just talking about the measurable isomorphism, you have a lot of freedom of disintegrating the space and gluing it again together to something topologically completely different. And this theorem is just, I think, a manifestation of that you still have a lot of freedom, and then you can just extract your measure and your measure preserving transformation and make everything back continuous and just kill all other measures. So this is just the result, but okay, we have a nice characterization of a class of so now we know that, and that's the point, that the systems which are equicontinuous, they may have many different topological models. So it is possible that you find topological models which are not topologically conjugate to each other. They are just isomorphic at the measured theoretical stage, and now mean equicontinuous just distinguishes some special subclass of models of those systems. And okay, so let us pass to yet another metric. So look at the definition of Besicovitch pseudometric. In the definition of Besicovitch pseudometric, we were just worried about average distance, okay? But we preserved order. And now let us consider yet another thing. So we have now two orbit segments of 2 points. So okay, okay. So before going maybe into much details, I just mentioned that there's yet another metric which is called Feldman-Katok. I was talking about this Feldman-Katok metric on a few occasions. So here I won't recall the full definition of this Feldman-Katok pseudometric, but I just mentioned a theorem we have with Felipe Garcia Ramos. So the theorem says that when you replace, okay, and for the Feldman-Katok metric, well, whenever you have a pseudometric, you can define a class of equicontinuous systems with respect to the pseudometric. So those are those systems, the original metric is continuous. So, so this is a theorem and we have that a minimal topological dynamical system is rho fk, so equicontinuous with respect to this Feldman-Katok pseudometric, even only if it is a topological model for loosely Bernoulli measure preserving system. So what is nice about this kind of theorem that, okay, if you ask somebody how to recognize, if you go into the wild and you will look after models of particular classes of measure preserving systems, then the characterization of something being a model for a measure preserving system is somehow external. You have to take your system, you have to find the simplex of invariant measures, and then if you find that your system is uniquely ergodic, then you have a chance to decide whether your unique invariant measure is isomorphic to, is in your class. So you have to leave your system, go to these invariant measures, and then you have a chance to decide whether there is an isomorphism or not. But your decision will be made on the purely measure theoretical considerations. But you can ask if there is an intrinsic, so internal characterization of minimal models for some class of systems. And we were quite surprised that with Felipe that we found such a characterization. And it's funny because it really means that if you just look at your system, then without checking actually any, you take a minimal system and it is enough to check this topological condition. It is enough to check if the certain pseudometric is continuous with respect to the initial metric. And if you check it, then you actually got the information about, okay, this system is a topological model for a class of loosely Bernoulli systems. So this class contains like this equicontinuity property is something which is true, for example, for every horocycle flow on a compact manifold. So because horocycle flows are uniquely ergodic, and this unique measures is well known due to the work of Marina Ratner to be really loosely Bernoulli, which means that this is maybe Bernoulli systems are loosely Bernoulli, but there are also other systems who are loosely Bernoulli, which are not Bernoulli. I'm not going into this way into those details. They are it is just a class which is a little bit more broader than the class of Bernoulli systems. So yes, but now I would like to go to the final pseudometric, and this is like in a sense kind of a ultimate pseudometric you can define going this way. So this is called mean orbital pseudometric, and we used to denote it as bar. And well, what do? You will again take limb soup at the very end, and before that, you take the infimum over all permutations in the set of all permutations. So Sn is the like symmetric group of the set 0, 1 up to n-1. And you take the infimum over all possible permutations of the following sum. So you look at the distance between J x and T sigma J y. So what you do is that you look at your orbits not as really sequences, but rather you consider them to be sets. So you really look for the permutation, like for the example I draw you, the permutation which maps so 0 to 2, 1 to 0, and 2 to 1, this permutation sigma seems to give us the smallest average distance between corresponding points. So I take one orbit segment and I put these points in the order, and I look for the optimal permutation of the points on the second orbit segment so that the mean distance between corresponding points after this permutation will be the smallest. And well, actually one can look at this. I don't have much time to describe it, but actually one can say that when you consider the empirical measure, so given a point x and time n, you may just consider the average of the Dirac measures concentrated at the first endpoints of the orbit and call it the empirical measure. And actually this distance we have here really looks like the kind of the optimal transport metric between those average between those empirical measures. So optimal transport metric on Wasserstein metric between those two empirical measures. And again, you go into limb soup, and okay, this metric was invented by Zhang and Zhang, and again, it was it turns out that this equicontinuity, so E bar equicontinuity, meaning that for every epsilon there exists a delta such that the initial distance between 2 points smaller than delta implies that the E bar distance between those 2 points smaller than epsilon, characterizes a few properties. So, well, actually, well, I'm talking about some results here I obtained with Tsai, Lee, and Habib Pourmand, but they are also recently two preprints which were published very recently, one by Xu and Zhang, and the other by Dovnarovich and Weiss. And as usual in mathematics, similar ideas, they like to appear simultaneously. So what I'm going to present is a theorem which is obtained by us, but part of the equivalences we have in that theorem was also obtained by the other authors. So so we have a theorem. Comfort, Dovnarovich, Weiss, and Xu Zhang. So this theorem says for a topological dynamical system Xt, the following conditions are equivalent. One, E bar equicontinuity. Second condition is that when you consider a family of maps, you take a point X and you associate to this point the empirical measure of length n to this point. And you take this family from n, so you have really a sequence of maps going from points to the Borel probability measures on your space. And this family is actually equicontinuous. This is equivalent to the equicontinuity. And then the third condition says, for every x in X, the orbit closure is uniquely ergodic. So the orbit closure of every point carries only one ergodic measure, and therefore every point generates exactly one ergodic measure, and this map of going from a point to the associated measure is continuous. For every point x in X, the map which takes a point and associates to it the set Vt of X. So this is a subset of measures on the space X, which are the not condensation, but accumulation points. Accumulation points of the sequence of empirical measures. And this is continuous when you consider this as a function from X to the compact connected subset of the space of all measures. 5, for every F in the space of continuous function, there exists a continuous function F star such that the sequence of ergodic averages converges to F star of X pointwise. And like 6, for every F in C of X, the sequence of measures So this is the sequence story not of measures but of functions. This sequence converges uniformly. So, okay, so we have another characterization of equicontinuity. And okay, I don't know if you know that or not, but this theorem has a nice corollary. Like this nice corollary says, well, we all know that when you have irrational rotation on the circle, then this system is uniquely ergodic. So the Lebesgue measure is the unique invariant measure. When we take rational rotation of the circle, the system is not uniquely ergodic. Every periodic point gives us one ergodic invariant measure. But now a nice observation following from that theorem is that, okay, this set of invariant measure for every isometry, in particular for the rational rotation, has to be a closed set of ergodic measures. It's like what you can get from this as the application. Okay, let me just finish by saying that I concentrated here during that talk on the equicontinuity conditions for those metrics, but those pseudometrics can be also used to checking that certain points are generic for ergodic measures, because if we are able to check convergence of a sequence of points to some limit point with respect to those pseudometric, then we can often conclude that if all points in our systems were generic for an ergodic measure, then the same has to be true. I'm sorry. The same has to be true for the limit point, which often saves a lot of work in that. Okay, I took too much time, so let me stop here. Thank you very much for your attention.
Thanks a lot, Dominic. Are there any questions?
I think I have a question. So my question is about like this E bar equicontinuity. You defined the pseudometrics there by basically interchanging the order on one of the partial orbits, right? Yes. And I was asking myself, if you go to group actions, so instead of acting with, for example, the natural numbers here, or the integers, and then you can also consider, for example, discrete amenable groups or even continuous amenable groups. So I was asking how to generalize this condition there. So for example, for the discrete amenable group, I assume you have two finite sets, so still you can take any kind of permutation there. But going to continue to for example, RD or something like this, letting RD act, you might want to add some continuity properties there. And I was asking how to do this.
So okay, the idea is there for this general actions. For the discrete actions, it's not a problem. You still permute over a finite set. For continuous actions, it's this Wasserstein idea is the key. Okay. So you can treat your orbit as a map from a group to the space, right? And now you take a compact subset of a group. You have a Haar measure there. Mm-hmm. If it is positive, you can normalize it and use your map to push forward the measure to the space. Mm-hmm. And then if you have two different orbits, you have two different push forwards. And you consider the Wasserstein metric between those two.
Okay, I understand. Thank you.
And then you just go to the limit with the growing sequence of compact subspace. Yeah, it is possible, but your Ferlin sequence, well, if your group is abelian, that you have that basically when your group is abelian, then the whole story can be repeated, I think, to the setting that Gabriel, Mike, and Daniel Lenz considered in their paper on mean equicontinuous actions. So then you have no problem. Yeah.
Thank you.
Okay, any other question?
I have one. So in the I think Bezikovich pseudometric, you take average on 1/n, right? And
yeah.
What happens if you take? What happens if you change the speed? So I don't know, 1/n square or 1/log n. So it changes the dynamics or not?
So okay, for sure you lose nice interpretation. Okay, so you if you change the averaging, then you no longer consider the distance between probability measures, right? Because when you keep, if you have n points and you keep averaging 1/n, then you may pretend that you are measuring as in a special way a distance between two probability measures, because you have this number of points and you divide by the same number, so the total mass of everything is 1. Okay.
Yes.
So if you lose that, you can still try to see what happens, but you lose an important feature. So I don't know. So this is what I be afraid. You in Z case you can still change you can take the logarithmic averaging, but then you have to change the weights you give to certain points. And there is something like logarithmic averages. So you divide it by log n, but you give weights like in the harmonic sequence. So you give weights like 1/1, 1/2, 1/3, 1/n to points along the orbit. And in this way, you still recover that you are dealing with some measures.
Okay.
So, I think that this is a nice question. What happens with a different speed? But the one word of warning, I think, because I don't know what happens. Maybe you can resolve that. But I think that what I have presented uses this fact that you still have measures after average.
Yeah, because in my mind, in the first metric, you obtain rotations on groups, right? And in the other metric, pseudometric, then you obtain extensions of those, right?
Yeah.
And well, so I was thinking if you change the speed, then you can obtain another class of dynamics. I don't know, which well, I don't know.
Yeah, so when as long as I keep some part of the order, I'm really take the extension of the groups. But in this last metric, we really completely, I think we lose this connection to groups. But for the first two, observation is right. Yeah.
Okay, thank you.
Okay, thank you. Anybody else?
I have a question.
Eric.
Yes. I would like to know if you always can assure the existence of topological model.
I'm sorry, could you repeat, please?
Yes. You define topological model there, but I was thinking if you can assure always the existence of that subsystem that is isomorphic to the general.
Yes. So the topological models for ergodic systems, they always exist. That's a theorem. They actually there are more theorems like that. One of the strongest theorem says that you can always find a topologically mixing minimal topological model for your ergodic system. This is also true for discrete amenable groups, although the proof was, I think, never actually published. I think a student of Benji Weiss did the proof and prepared a preprint, and the preprint was accepted even in the ergodic theory and dynamical system. But as far as I know, he never sent back the corrections, so it never went behind that. But the existence of topological models is true in a good generality. You also have works on models for models for non-ergodic systems. And well, Till wants to know how about unimodular amenable groups, so groups like Rn. Then I don't know. I think one should ask Benji. If there is some result, then Benji should know.
Okay, thank you.
Okay. Anybody else? Anybody else? So if not, then let us thank Dominic again for his very nice talk. Thank you, Dominic.
Thank you very much.
Thank you. So we have a lunch break in Brazil now, maybe some coffee break in other countries, but we return at 2 Brasilia time with Obata, and at 3 we have the talk of Pacifico, also known as Zezé. And after the talk we will have our toast, so get ready. So it's nothing, Zezé was asking earlier how it would be, it's nothing very fancy. It's very rudimentary, actually. Each person just brings her or his own glass, and we drink together the way that we can, that is virtually now. Okay, so see you afternoon. Thanks, Dominic, for the talk. It was great.
Thank you very much. Yeah.
So we return at